We went through that process of identifying a strictly dominated strategy. A strategy for which an alternative always gives a higher path. Always gives a higher path. Now I want to give you another game. And this game, we'll present it in an abstract form, but this is a game played out between the US Air Force and the Japanese Navy in March 1943. And we'll call it the Battle of the Bismarck Sea. So if you know your geography, just above Australia in the South Pacific, you've got the Bismarck Sea. And so, what happened in this game is the Japanese Navy wanted to transport their troops across the South Pacific. The US Air Force didn't want them to do that. They wanted to send their planes out to bomb them. So, the Japanese Navy had two available choices. They could either take a northern route across the South China Sea, or across the South Pacific, or they could take a southern route. Now, the northern route was much shorter. It's much quicker. The southern route was the longer path. So that's what the Japanese Navy, their first consideration. Do we go to the north, or do we go to the south? The problem is, regardless of what route they took, they would then be susceptible to being attacked by the US Air Force. And obviously, the longer path they took, the longer would their ships and troops be exposed on the sea, and the more dangerous it was for them, and the more damage could be inflicted. So, they need to decide, do they go to the north or the south? North is shorter, south is the longer path. So that's the choice of the Japanese Navy. The alternative then is the US Air Force. What they want to do is identify the ships carrying troops and then bomb them. But they want to have as long a time to be able to bomb them to inflict as much damage as possible. So what they would rather is the maximum time available. They would much rather, you can see the obvious logic here, they would much rather have the Japanese ships on the water as long as possible. But they need to identify them. And so what they did, is they send out their scout planes to identify exactly where the Japanese troop ships were. So they could either send their planes, their scout planes, to the north or to the south. They could either send them to the north or the south. Now, if they sent them to a path where the Japanese Navy didn't have their ships, they would then have time to then come back and go down the alternative path. But if they did that, they would lose bombing time and then have a less opportunity to inflict damage. So that's the basic scenario. So both our players, as we've represented it here in its normal form, we've got the US Air Force and we have the Japanese Navy. And both of these players are choosing over one of two available strategies. And these are to go north or south. North and south. And then all we've done is put the numbers in to rank the preferences. And the numbers we have here are 1, 2, and 3 for the US Air Force, and -1, -2, and -3 for the Japanese Navy. Now, I'll run through the scenario for the US Air Force first of all, and then I'll say something about the comparable preferences, payoffs for the Japanese Navy. So, we can see the US Air Force, the most preferred outcome, where it gets a payoff of 3, is where it sends its planes along that longer southern path, and the Japanese Navy also sends its ships along that longer southern path. It finds the ships immediately. It has the maximum time to bomb the Navy. So that's its most preferred outcome, and hence it would give its payoff of 3. Now, the second most preferred outcome, where they have a payoff of 2, is, firstly, if the US Air Force goes along the shorter northern route, and the Japanese Navy also goes along that shorter northern route. It has less opportunity to bomb them and inflict damage than it goes along the longer southern route, but it identifies them immediately. What also gives a payoff of 2, what's equally preferred, is if the US Air Force initially goes along the northern route, but the Japanese Navy goes along the longer southern paths. So initially, it can't find the ships. Patrol planes then come back in, and then they go out down the alternative path. That gives exactly the same payoff of 2. The least preferred outcome, the absolute least preferred outcome, is where the Japanese Navy goes down the shorter northern route, and the Air Force initially goes down the southern route. The planes go out, they can't find them, they've got to come back in. I think my idea of getting anyone to sit on one side is probably going to fall apart. Never mind, don't sit too far on the corner, you can just sit on the edge, please. So they go down the US Air Force go down the longer route first of all. The Japanese Navy aren't there. They then send their planes out for a second time to spot them. They find them, but they're on the shorter route. Given that their planes spent time going down the wrong route initially, they've got less time to bomb them, less time to inflict damage. And hence, that's the least preferred path. So, in terms of these combinations, you've got a 3, a 2, and a 1. And all I've described is the scenario what the US Air Force would prefer. Now, what we've got here, I won't spend too much time describing this type of game for the moment. I'll pick up upon it in next week's lecture and say a little bit more. But this game here is what's called a zero-sum game. And it's for fairly obvious reasons. This is a game, a type of game, where the absolute only way one player benefits is at the direct expense of the other player. There's only a certain amount of payoff for any combination of actions. And the players are going to split it. What one player gets is directly at the expense of the other. And why is it called a zero-sum game? Because if you sum all of the outcomes, they're going to come to 0. So, for example, this outcome of 3 for the US Air Force there, well, if the US Air Force is getting a payoff of 3, that can only come at the direct expense of the Japanese Navy. So if the US Air Force get +3, the Japanese Navy get -3. And all of the other outcomes have a comparable interpretation. So this, if that's the most preferred outcome for the US Air Force, it must be the least preferred outcome for the Japanese Navy. If this here, south-north, is the least preferred outcome for the US Air Force, that must be the most preferred outcome. It's the least negative number, must be the most preferred outcome for the Japanese Navy. So that is the game that we've set up. It's just an abstract game it's just a game that we've set up in an abstract manner, and we can identify outcomes using the same principles as before. So, what did we say? We said in order to identify the iterated dominance equilibrium, we need to identify a strictly dominated strategy. Can anyone see the strictly dominated strategy? Is there a strictly dominated strategy in that game? I'll give you a few moments to look at it, but simple. If it was, it would be straightforward. But there isn't a strictly dominated strategy in that game. For example, I'll just take a very, very quick one. If the Japanese Navy went north, what would the US Air Force do? Would they go north or south? They would go exactly north, because they would get a payoff of 2, as opposed to a payoff of 1. But what would happen, though, if the Japanese Navy went south? Would the US Air Force go north or south? They went north, they get a payoff of 2. They went south, they get a payoff of 3. So again, this time, they would go south. So neither north nor south strictly dominates the other. What the US Air Force would choose to do would depend upon what the Japanese Navy did. Okay? So that's for the US Air Force. What, though, about the Japanese Navy? Well, would they choose to go north or south when the US Air Force went north? They would get the same outcome under either scenario. They get -2, so they wouldn't mind. But if the US Air Force went south, what would the Japanese Navy do? Choose to go north. But in that sense, is there a strictly dominated strategy? Is there a strategy that always gives an inferior outcome? No. What there is, though, is a weakly dominated strategy. And in this sense here, south is weakly dominated by north. So when we talked about dominated strategies before, we said a strictly dominated strategy. A strategy that always gives a lower payoff. And as such, we could then eliminate it. Here, though, it's subtly different. We have a weakly dominated strategy. South is weakly dominated by north. So we're not saying that south always gives a higher payoff. We are saying that north never gives a lower payoff. Slightly different, subtly different. So it gives a higher payoff when the US Air Force goes north, but it gives exactly the same payoff when the US Air Force goes to the north. So in this sense, we say it is not a strictly dominated strategy, but rather it's a weakly dominated strategy. But we can adopt the same sort of tools. We can say that a rational player would never play a weakly dominated strategy, and hence we could exclude it. And so if we exclude that from the potential options of the Japanese Navy, and you can see what's happening here. What the Japanese Navy don't want to do is, what they didn't want to do was ever run the risk of having that worst possible payoff, sending its troops down the long route to the south. Hence, that's what they did. They wouldn't choose to ever go to the south. And appreciating that, then the US Air Force said, well, understanding that the Japanese Navy aren't going to take that longer path, do we send our scout planes to the north or to the south? We send them to the north, we get a payoff of 2. Send to the south, we get a payoff of 1. And so, what they chose to do was send their planes to the north, at the same time as the Japanese Navy sent their troops across that northern path. And in March 1943, that's the exact game that was played out. And so, again, using the same principle, we arrive at a single outcome, a single plausible outcome, an iterated dominance equilibrium. So of the 4 potential outcomes, the one that actually does occur through this process of eliminating dominated strategies is our iterated dominance equilibrium. So, those were 2 games that we've just described that shows how this idea of outcomes can be brought about by using the idea of dominated strategies, either weakly or strictly. However, this whole process does have a number of drawbacks. It has 2 inherent drawbacks. And the first one is that this whole idea of identifying an iterated dominance equilibrium lies upon the idea of rationality. Each player needs to be rational. Each player needs to act rationally. They need to appreciate the whole concept of rationality. And obviously, the more steps we go through, the more stringent do these requirements about rationality be. Not just the players understand rationality, but they fully adhere to all of these notions of rationality. If, for whatever reason, any of the players ever acted in an irrational way, this whole process would fall down. So that's the first problem. with this process of iterated dominance equilibrium. It does rely very, very strongly upon this notion of players acting rationally and understanding the idea of rationality at all times. Probably even more problematic, though, is the fact that this process of iterated dominance equilibrium often leads to imprecise predictions. Now, when we went through that first abstract game today, and when we went through the prisoner's dilemma, and when we went through that game of the Battle of the Bismarck Sea, it wasn't a problem. We had our games, we had multiple potential outcomes, but there was always one iterated dominance equilibrium, a single outcome. However, that's not always the case, and in many instances, that will not be the case. So, look at the following game. You've got your handouts? Yeah, I mean, it is in the notes, but if anyone not got a handout, save your copy down for 1 minute. Okay. So, could you pass them? Thank you. A couple behind you as well. Okay. That's, for the moment, we're not really, apart from looking at it, you're not going to write anything on that game. Because, it's just the one. As I said, for the moment, you're not going to write anything. And the reason, we're going to come back to this game a little bit later, and the reason you're not going to write anything is because there are no dominated strategies. There are no strictly nor weakly dominated strategies. So what did our process of identifying the iterated dominance equilibrium rely on? You've got to identify a dominated strategy. Then you remove it. And then we iteratively move through until we arrived at our unique outcome. Well, this game says, this abstract game says, you have two players. Player 1 and player 2. Player 1 choosing over top, middle and bottom. Player 2 choosing over left, centre and right. So, we start off saying there are 9 possible outcomes. This is the game played out between these two players. 9 possible outcomes that it could be. Which one is it? Actually, we don't know. There are none of these outcomes that we can exclude. Hence, they're all iterative dominance equilibria. And that isn't particularly helpful. So, what does that suggest? Well, it suggests that we need something else. If we're going to look to define equilibrium outcomes in a much wider class of game, a much broader class of game that we've seen already, we're going to need something else. And that something else is the ability to define a Nash equilibrium. And a Nash equilibrium is a much stronger, a much stronger equilibrium concept than we've seen thus far. So, a Nash equilibrium. What is a Nash equilibrium? Well, let's think, what's the starting point? We've got players in our games. If players act rationally, what are they going to do? They're going to look at the available strategies, look at the available choices they can make, and they're going to choose a best response. They're going to choose their optimal strategy. They're going to choose what's best for them. That's the theory of rational choice. That's what rational people do. You choose what's best for you. But you will want to choose, our rational player will want to choose what's best for her, given her beliefs about what the other rational players in the game will also choose. And what's the most plausible belief about other rational players? That they too will also choose a best response. So, bring all this together then. We've got these rational players within the game, all thinking about what their fellow players are going to do. And their ideal is to choose an action that's a best response for them. Put it all together, and what does it mean? Well, you put it all together, and that is what our Nash equilibrium is. It will mean that we have an outcome a situation where all players within the game are choosing a best response, are choosing an optimal strategy. And these are best responses to the best responses chosen by all of the other players within the game. So everyone is choosing something that's optimal. Given what you can do, given what you think the other player is going to do, the Nash equilibrium that exists in any game will be described by the fact that all players are choosing a best response. And if we take that definition, think, what does it mean if we had a set of outcomes that were not a Nash equilibrium? Would that represent a plausible outcome? Well, think about our definition. We said in a Nash equilibrium, all players are choosing best responses. So, if we had an outcome that isn't a Nash equilibrium, by definition, what does that mean? It means at least one of the players is choosing an outcome, is choosing a strategy that is not a best response. So if that player is doing something that is not optimal, is not a best response, what incentive will they have? They will have an incentive to change, to do something else. And if they're going to change, if they're going to do something else, we cannot have an equilibrium outcome. Hence, an outcome that is not a Nash equilibrium is not plausible. And the flip side is, what does it mean by an outcome that is a Nash equilibrium? Well, an outcome that is a Nash equilibrium will mean that all players are choosing a best response. And if all players are choosing a best response, does any player have an incentive to deviate, to do something else, do something different? Obvious answer is no. Hence, that's why it's an equilibrium outcome. Because in a Nash equilibrium, no player has an incentive to deviate, has an incentive to do anything different. That then is our idea of a Nash equilibrium. Now, it's utterly important for this module going forward that you really understand and appreciate what a Nash equilibrium is. It's also important that you're able to identify Nash equilibrium, Nash equilibria, in a whole raft of games. Any game, potential game that you might possibly see. So, to that end then, what I'm going to do is run through some examples. And the first one is just revisiting that game that we saw previously. That abstract game that we said that the process of the iterated dominance equilibrium didn't provide any useful predictions. Because it said that everything was a possible outcome. So, that's our game. How do we identify a Nash equilibrium? Well, in any game that we could represent in its normal form, the process of identifying a Nash equilibrium is always the same. And it's really, really straightforward. So, I'll go slowly initially, just to get used to the mechanics, but this is really, really easy. I'm not necessarily interested in an exam, in you being able to identify the outcome per se. I'm interested in you being able to interpret it and understand it and describe to me why it's a Nash equilibrium. But in a game such as this, the way in which we'd identify a Nash equilibrium is very, very straightforward. We would say, for each player and each possible strategy of that player, what is the optimal response or the best response of the other player? So, we could say for player 2, and all the options, all the strategies that player 2 can choose, and player 2 can choose over left, centre and right. If player 2 chooses these, what's the optimal response? The best response from player 1. And that's all we do. So, let's say if player 2 chose left. What would player 1 choose to do? Check it out. Remember, player 1, so what we're doing, we're looking at the first figure. The preferences, as we said last week, the first figure is our role player. The second figure is our column pair. So, if player 2 chose left, player 1 would choose over top with a pair for 0, middle with a pair for 4, or bottom with a pair of 3. Well, obviously, middle gives the best pair. So I'll just put a circle around that to denote that it's an optimal response. If player 2 instead chose centre, the optimal response from player 1 is top with 4, or middle with 0, or bottom with 3. Obviously 4 is the most preferred outcome, so there you go. I'll put a circle around that. So if player 2 chose centre, the optimal response from player 1 would be to choose top. And then lastly, if player 2 chose right, player 1 would choose bottom, exactly 6, pair for 6, as opposed to 5 in either of the other scenarios. And that's it for player 1. We've identified all of the best responses for player 1. Now let's do it for player 2. What are the optimal responses from player 2? Remember, what player 2 chooses, is dependent upon the choice of player 1. So if player 1 chose top, what would player 2 do? Here, can you see it? Left gives a pair for 4, centre gives a pair for 0, right gives a pair for 3. So there you go. Our optimal response is left. So I'll put the circle around the 4 to denote the optimal response. If player 1 chose middle, player 2 is going to choose centre, exactly with a pair for 4, higher than either 3 or 0. And then lastly, if player 1 chose bottom, player 2 is going to choose right. 6 is higher than either 5 there or 5 there. And so, what does that suggest? It suggests that there is a single set of outcomes where both circles coincide. Now, what do those circles denote? Those circles denote a best response, an optimal response from one of the players. But there's only one cell where both of these circles coincide. Hence, there's only one combination of strategies where both players are choosing a best response. And what was that? Where both players are choosing a best response is a Nash equilibrium. Hence, in that game, there is a single Nash equilibrium outcome, where player 1 chooses bottom and player 2 chooses right. And all of the other potential outcomes, because they contain either a single circle or no circle at all, means that they are not Nash equilibria. And if they're not Nash equilibria, they're not plausible outcomes, because at least one of the players would have an incentive to deviate, would have an incentive to do something else, because they wouldn't be choosing an optimal response. So, for example, purely as an example, let's take that one there, middle centre. There's only a single circle. It's not a Nash equilibrium. I'm telling you, it's not plausible. That won't be the outcome, that couldn't be the outcome of the game. Why is it? Think about these incentives to deviate. If player 1 were to choose middle, does player 2 have an incentive to deviate? Yes or no? Player 2. Don't nod your head. No. Player 2. Player 1 is choosing middle. Player 1 chooses middle. What's the optimal response from player 2? To choose centre. So player 2 is choosing optimal strategy. Player 2 has no incentive to deviate if player 1 is going to choose middle. So for player 2 it's fine. But the point is, player 1. Does player 1 have an incentive to deviate? Well, if player 2 is choosing centre, would player 1 want to remain choosing middle? Yes or no? No. Because if they choose middle, if they remain choosing middle, they get a pair for 4. They would have, player 1 would have an incentive to deviate. If they chose top instead of middle, the outcome would go from 0 to 4. And so does player 1 have an incentive to deviate? Yes. Hence, that outcome there cannot possibly be a Nash equilibrium. And hence, if it's not a Nash equilibrium, it's not a plausible outcome. And I've used that middle centre purely as an example. The exact same logic would apply to every other cell where there's only a single or no circle at all. At least one of the players has an incentive to deviate. And if we look at the Nash equilibrium at bottom right, does either player have an incentive to deviate? Well, they can't do. Neither player can make themselves better off by doing something different. Therefore, they have no incentive to deviate. And hence, that is an equilibrium outcome. There's no reason why we would move away from it. And hence, in this game here, guided by that principle of Nash equilibrium, we've now arrived at a single unique outcome. That one of bottom right. Now, as I alluded to a little bit earlier, I said that the idea of a Nash equilibrium is crucial in game theory. It's the starting point in game theory. So, what I'm going to do for the rest of this first half of the lecture is just run through some examples, some more classes of game, and use this as an opportunity to show you more types of game, but also give you the opportunity to identify the Nash equilibria that exist in these games. And the first game that I'm going to look at isn't actually a new game. What we're going to do is revisit that game that we saw last week, that game of the prisoner's dilemma. And the reason, though, we're going to revisit it is because I want to show you the prisoner's dilemma that we saw is not just a game, it's a class of game. But I'm going to put a slightly different interpretation upon it this time. So the interpretation that I'm going to put on the prisoner's dilemma this time is that we have a group of students, we have two students working on a joint project. And these students can put in one of two levels of effort. They can choose one of two available strategies. They can either work hard with their fellow student on the project, or they can shirk, not get involved at all, and don't put any effort in. So this is the game that we've got. Two students, do they either work hard or shirk? So in its normal form, this is what the game would look like. So let's say that our two students are Bill and Ben. And Bill and Ben choose over their available strategies of work hard or shirk. Work hard or shirk. And all we've done with the numbers in this normal form representation is just rank the outcomes. And the numbers that I've used are 0, 1, 2, and 3. And this game is purely symmetrical. Whatever applies for Bill is exactly the same for Ben. It's totally and utterly symmetrical. So let's just run it through using Bill as our example. His most preferred outcome, where he gets the payoff of 3, what he would love to happen is that if he puts no effort into working on this project, if he shirks, but his fellow student, Ben, works hard. When that's done, the project's completed, Bill puts no effort in, he free rides, but he gets all of the benefit from it. So that's his most preferred outcome. That's where he gets his highest payoff of 3. Now the second most preferred outcome, where he gets a payoff of 2, is where both of them work hard on the project. So if they both work hard, the project gets completed. It's of an even higher quality than if only one of them works hard. But that extra effort that Bill has to put in doesn't compensate him for the extra effort he needs to expend. So that's his second most preferred payoff. Next, in terms of outcomes, is where, payoff of 1, and they both choose to shoot. Where neither of them puts any effort in whatsoever, the project doesn't get completed, and they both fail. But that isn't the worst outcome. The absolute last thing that either Bill or Ben wants, and that's where they get the payoff of 0, is to think that the other person has got one over on them. The absolute last thing they want to happen is to work hard on the project at the same time as their fellow student has done absolutely no effort, has put in no work whatsoever. They don't want their fellow student to free ride and get all the benefits for their hard work. So that is absolutely the least preferred outcome. And you can run through it, as I said, it's symmetrical, exactly the same comparable preferences for them. So that's the game of the prisoner's dilemma. Where's the Nash equilibrium? Well, let's very quickly run through that rubric then. For each player and each possible strategy of that player, what's the optimal response, the best response of the other? Well, let's take Ben. If Ben works hard, what's Bill going to do? Work hard or shirk? Shirk, yep. If Bill works hard, he gets a payoff of 2. If he shirks, he gets a payoff of 3. So I'll put the circle around the 3 to denote that's an optimal response. However, if Ben shirked, what would Bill want to do? Work hard with a payoff of 0 or shirk with a payoff of 1? Shirk with a payoff of 1. So again, put that circle around there. So regardless of what Bill does, regardless of what Ben does, Bill will always choose to shirk. But if you think about the discussion that we had about the prisoner's dilemma last week, what was the key feature of the prisoner's dilemma? That there was a dominant strategy, something that you would always choose to do. Well, here, doesn't matter what Ben does, Bill will always choose to shirk. He always gets a higher payoff. So, that's for Bill. Let's find Ben's optimal strategies. So if Bill chose to work hard, what's Ben going to do? Shirk. Again, work hard gives a payoff of 2. Shirking gives a payoff of 3. If Bill chose to shirk, Ben is going to shirk again. Payoff of 1 as opposed to a payoff of 0. So what does that mean? That means in this game of the prisoner's dilemma, there is a single, unique Nash equilibrium, where both players choose to shirk. But again, this accords perfectly with what we said previously when we first introduced this game and we looked at the idea of an iterated dominance equilibrium. There's a dominant strategy in the game. There's only one strategy that both players will choose to pursue. And if you think about it, this Nash equilibrium that we have here must include that dominant strategy. Because we said in the Nash equilibrium, players are choosing a best response. All players are choosing a best response. And what is the dominant strategy? That's always the best response, regardless of what the other player does. So that logic would mean that dominant strategy that we identified previously must be part and parcel of that Nash equilibrium. But notice, though, how this idea of a Nash equilibrium is exactly the same outcome that we did find with the iterated dominance equilibrium. So obviously, there's a relationship between these two equilibrium concepts. But what I want you to do is pick up upon a point that I said maybe 10 minutes ago, when I introduced you to this idea of a Nash equilibrium. I said we needed something else to identify outcomes in a much wider class of things. That something else was a Nash equilibrium. And I said the Nash equilibrium is a much stronger equilibrium concept than we've seen before. So, now we're in a position to say, why is it a stronger equilibrium concept? Well, it's stronger in the sense of two ways. Firstly, and for the moment, I'll just tell you what these points are, and then we'll go back to the example and I'll explain what these points are. So firstly, a Nash equilibrium will always survive that iterated dominance equilibrium process. So that process we went through, identifying strictly or weakly dominated strategies. If you do that, the Nash equilibrium will always survive that process. You would never exclude the Nash equilibrium. So that's point one. The second point, though, is that there may well be strategies that survive that iterated dominance equilibrium process that do not form any part of a Nash equilibrium. And why is that problematic? Because I've already said that if an outcome is not a Nash equilibrium, it's not plausible. Hence, if there are outcomes identified by that iterated dominance equilibrium procedure that identify outcomes that are not Nash equilibria, these outcomes are implausible. Hence, is that the sort of procedure that we want to be using that identifies implausible outcomes? And so it's for those reasons that the Nash equilibrium is a much stronger equilibrium concept. So, that's an overview of those 2 points. Everyone finished copying those bullet points down? Yeah? Okay. So, let's return then to that abstract game that you've got on the handout. Now, when we looked at this previously, we said of these 9 potential outcomes, iterated dominance equilibrium, which ones are identified? They all were. So, that was point 1. Because the Nash equilibrium was that one there, bottom right. So, we said that this process of the iterated dominance equilibrium would never exclude the Nash equilibrium. That was the first point. Well, that's true. That's the Nash equilibrium. Does the iterated dominance equilibrium process exclude that? No. So that was point 1. However, not only did this iterated dominance equilibrium leave that Nash equilibrium, it also left all of these other outcomes there. And what did we say? We've said that they're not Nash equilibria. If they're not Nash equilibria, they're not plausible outcomes. So this whole idea of going through this process of the iterated dominance equilibrium, or identifying the iterated dominance equilibrium, yes, it leaves one plausible outcome there, bottom right, but it also left 8 other implausible outcomes that were not Nash equilibrium. And hence, that's why we say a Nash equilibrium is a stronger equilibrium concept, because it doesn't identify all of these other implausible outcomes. Outcomes that we know rational players would never choose, because if they're not Nash equilibria, the players will have an incentive to deviate. If they've got an incentive to deviate, it cannot be an equilibrium outcome. And we said that the Nash equilibrium is a stronger equilibrium concept, than the idea of a iterated dominance equilibrium. But in this game, there was a Nash equilibrium. Is that purely coincidental? Or is it something that we'd expect to find? Well, we would expect to find it, because in every finite game, and this is a finite game, and by a finite game, I mean that there are a definitive number of players choosing over a definitive number of strategies. So, in any finite game, there will always be at least one Nash equilibrium. Now, this is known as the Nash theorem. Now, the proof of this is pretty complicated, so you can just take my word for it. I'm not going to go through the formalities of that, but if we've got a game that looks like this, where we've got a definite number of players choosing over a definite number of strategies, there will always be at least one Nash equilibrium. And in this game here, there was one Nash equilibrium. But notice the language that I used. There will always be at least one Nash equilibrium. Now, by the very nature of those words, doesn't it suggest it might just be possible to have games where there are multiple Nash equilibria, where there is more than one Nash equilibrium. But is that the case? Well, let's look at the following game. And the following game is known as Battle of the Sexes. Now, if you remember the prisoner's dilemma, what lies behind this, the tension in the prisoner's dilemma, is whether the players choose to cooperate with one another, whether they choose to work hard, whether they choose to deny. It's a game of cooperation. Do you cooperate or not? Well, in this game of the Battle of the Sexes, this is a game where the players involved absolutely want to cooperate with one another. However, in the Battle of the Sexes, the players disagree over the best form that cooperation should take. So, in this game of the Battle of the Sexes, it relates back to its original exposition, relates back to the 1950s. And when I explain the game in a few moments, that will become obvious. And in this game of Battle of the Sexes, a man and a woman are deciding upon where they want to go out for their evening's entertainment. And remember, what lies at the heart of this game is that they want to cooperate with one another. They want to go to the same venue. That's what they want to do. So, the choices of venue, though, where they're going to spend their evening's entertainment, are either to go to the opera or to go to the prize fight. And absolutely, they want to go together. They don't want to go to separate venues. They want to go together. However, we're going to finish with that one? Yep. However, it's the man and the woman disagree over their most preferred venues. According with gender stereotypes, what we know is the woman would much rather go to the... You think it's going to be? Opera, well done. And the man would much rather go to the prize fight. Okay? That's what's going on the next slide. So, they agree that they want to go together. Given that tomorrow is Valentine's Day, it couldn't be probably a better example to use. So, they're choosing, do we go to the opera together, or do we go to the prize fight? The man absolutely would much rather that they spend the time together at the prize fight. That's his most preferred venue. They have the choice, what do you want to do? I want to go to the prize fight. However, the woman would much rather that they spend the evening together at the opera. Right? So that's the game that we've set up. Again, a game of coordination. Where do they choose to go? Absolutely. What they don't want to do is be apart. They want to spend time together. But the man's most preferred outcome is the prize fight. They go together to the prize fight. The woman's most preferred outcome is that they go together for the opera. Now, what I've done here, and indeed I'm going to do it in most of the examples in this course, and again, it's something that I'm going to get you to do in seminars, and it's the sort of thing that I'm going to get you to do during the exam as well. What have I done here? I've told you the game. I've given you everything you need to set this game up in its normal form. In normal form, we need three things. We need the players. We've got the man and the woman. We need their strategies. We've got opera and prize fight. But we also need their preferences, their paths. Well, I've just described them for you there. I've told you what the man and the woman want. They want to go to the same venue. But the man would prefer that they go to the prize fight together. The woman would prefer that they went to the opera together. So I've set this game up for you. What I would expect you to be able to do in an exam, and we'll practice this again in seminars, is take all of that discursive information, all of that textual information there, and then represent that game accurately in its normal form. If you think the way that we're doing this in lectures, I'm setting it up, and then we jump in to the game. That's what I expect you to be able to do for that next step. Okay? So this then is the next step. I've set the game up for you. I've told you everything that you need to know. That would therefore be an accurate representation of this game in its normal form. So, we have the players, the woman and the man. We have their available strategies, opera and prize fight. Those are the easy parts. You would then be expected to put these numbers in here. So, all we've got are the outcomes of 0, 1 and 2, these numbers. And all they will do is rank the outcomes. So, a 2 means it's the most preferred outcome. And for the woman, what was her most preferred outcome? That they both went to the opera together. And so for the woman, remembering for the woman that her payoffs are the first figure, that's where she gets the 2, where they both go to the opera. For the man, what's his most preferred outcome? That they both go together to the prize fight. So there you go. When they both go together to the prize fight, the man, the second figure this time, gets his highest payoff of 2. And then for the woman, her second most preferred outcome is where they go to the prize fight together. For the man, his second most preferred outcome is that they go to the opera together. And if they go to different venues, that's the worst possible outcome. So here, when one goes to the fight and the other goes to the opera, and vice versa, they both get their least preferred outcomes of 0. And that is the battle of the sexes. So, how would we identify the Nash equilibrium? For each player and each possible strategy of that player, what's the best response of the other? So very, very quickly, hopefully you've all got the hang of this now. Again, I'll reinforce this in seminars, or on the seminar on Wednesday also. So, if the man chose to go to the opera, what would the woman choose to do? Also go to the opera. Payoff of 2 is preferred to a payoff of 0. If the man chose to go to the prize fight, the woman would choose to go to the prize fight also. 1 is preferred to 0. And that's it. Those are the best responses for the woman. And then for the man, if the woman chooses to go to the opera, the man goes to the opera and gets a payoff of 1. Is he going to go to the prize fight and get a payoff of 0? No. Obviously, he chooses also to go to the opera. And then lastly, when the woman goes to the prize fight, the man will also go to the prize fight. So hence, 2, or because 2 is preferred to 0. And what does that mean? Well, of the 4 possible outcomes that this game could arrive at, there are 2 of them where both circles coincide. And hence, that would mean that there are 2 Nash equilibria. One where they both go to the opera, and the other one where they both go to the prize fight. Of those 2, though, which is more plausible? Well, neither. They are both plausible outcomes. Now, we know these ones, where they go to different venues, are not plausible, because both players would have an incentive to deviate. They cannot be equilibrium outcomes. They are not Nash equilibrium. But of the 2 Nash equilibria that we have identified, when they both go to the opera, the woman has her most preferred payoff, has her best outcome. When they both go to the prize fight, the man has his most preferred outcome. But at the moment, when we look at this game and those 2 Nash equilibria, are either of those Nash equilibria more likely? The answer is no. This is just a game where there are multiple Nash equilibria, and we couldn't say for sure which one would be the most likely outcome. However, what I want to do is take that on board and now look at the next game I'm going to give you. And again, there will also be multiple Nash equilibria. But in this next game I'm going to show you, one of the Nash equilibria is more plausible, is more likely than the other. And this next game is called the Stag Hunt. And in the Stag Hunt, what the game revolves around is a group of hunters who are involved in the pursuit of a stag. Now, within this game, each of the hunters will be given a specific duty to perform. They will have a specific task to do on this hunt. And they must all the hunters on this hunt, must remain attentive. They must dutifully apply their duties in order for the hunt to be successful. If any of the hunters doesn't pay attention, the stag will get away. However, each of the hunters has an incentive not to pay attention, not to pursue the stag, not to do what they're supposed to do, and instead go off chasing rabbits. Now, if one of the hunters decides to go off and chase rabbits, he is absolutely guaranteed to catch that rabbit. But what is also guaranteed is that the stag will escape. So, that's the game. So each hunter needs to decide, do they go chasing rabbits or do they pursue the stag with the other hunters? Now, in terms of the outcomes, what all of the hunters would prefer is to have a share of the stag, is to catch the stag, and they will then share that equally, and all of the hunters would much prefer that to having a rabbit. So a share of the stag is preferable to having the single rabbit. However, both of those outcomes are more preferred than being left empty-handed. To pursuing the stag, but the stag gets away. So you don't get the stag, you haven't gone off chasing rabbits, you're left with absolutely nothing. That's the worst possible scenario. So again, what have we done? I've set the game up for you, I've told you all the information that you need to now describe this game in its normal form. Now, in an exam, I probably wouldn't give you this exact game, because this is a standard game that we've got from lectures, but it's the same basic idea. You've got everything you now need to represent it in its normal form. We've got the players, we've got the strategies, and we've got the outcomes, the preferences. So, given that then, what we'll do is take a two-player version of this game. So you've got two hunters, Hunter 1 and Hunter 2, and the available strategies of these hunters are to pursue the stag or go off chasing rabbits. So pursue the stag as in remain attentive to the hunt, or don't remain attentive and go off chasing and hunting a rabbit. So we said for both players the most preferred outcome was to get a share of the stag. And the only way this will happen is if both hunters pursue the stag, if they both remain attentive. So our highest number here is 2. And so both players will get their more preferred outcome if they both remain attentive and pursue the stag. So both players get the highest payoff in that top left-hand corner. Now, otherwise, the next preferred outcome is if they catch a rabbit. So, for Hunter 1, if he pursues a rabbit, he'll get a payoff of 1 there. He will get a payoff of 1 there. It makes no difference what the other player does. If he chases a rabbit, he's guaranteed to get it. So that will always give him a payoff of 1. And then for Hunter 1, the worst possible scenario is if he pursues the stag whilst the other player pursues the rabbit, he's left empty-handed, doesn't get a rabbit, and the stag gets away. So that's it for Hunter 1, and for Hunter 2, it's exactly the same. It's symmetrical. Yep. So he gets his most preferred payoff of 2 there, and if he pursues a rabbit, here he always gets a payoff of 1. And there, that's his worst possible outcome, where he pursues the stag gets away, and he doesn't get a rabbit. So that's the game that we've set up. Where would the Nash equilibrium be? I'll do this really, really, really quickly. Okay? And in your own minds, please do it as well. So, for Hunter 2, if he pursued the stag, the Hunter 1 would also want to pursue the stag. 2 as opposed to 1. If Hunter 2 pursued the rabbit, the optimal response from Hunter 1 is also to pursue the rabbit. 1 as opposed to 0. And that's it for Hunter 1. Now, what are the optimal or the best responses for Hunter 2? If Hunter 1 pursues the stag, Hunter 2 will also want to pursue the stag. 2 as opposed to 1. And then lastly, if hunter 1 pursued the rabbit, hunter 2 would also want to pursue the rabbit. 1 as opposed to 0. So, as we saw, I did rush through that a bit. I wasn't too quick for anybody. We are going to go through things like this again, or you are going to go through things like this again in seminars. We're really, really, really going to reinforce this. But this is the game that we've got, and just in the same way as we saw with Battle of the Sexes, there are 2 Nash equilibria. One where they both pursue the stag, and the other where they both go off chasing rabbits. So this accords with this idea of the Nash theorem. In a finite game, it's what we've got here, there will always be at least 1 Nash equilibrium. Is there at least 1? Yep. In fact, in this game, there are 2. Different, though, to Battle of the Sexes. In the Battle of the Sexes, we had these 2 outcomes. Both go to the opera, both go to the prize fight. In one was better off, in the other one, the man was better off. But we say, look, neither of these outcomes is more likely. In this game here, though, look at the 2 outcomes. Here, that one there, where they both pursue where they both pursue the stag. It gives a higher payoff. Both players are better off. That in itself suggests itself as a more likely outcome. There are 2 possible Nash equilibria, but that one where they're both better off suggests itself as more likely, as more plausible. And when that happens in game theory, we describe it as a focal point. Of all of the outcomes within this game that we could gravitate towards, which one do we actually gravitate towards? Which one do the players gravitate towards? Well, in this game of the stag hunt, this one here, where both players are better off, suggests itself as a more likely outcome. And when that happens, it's described as a focal point. Now, for the rest of today's lecture, I want to pick up on this idea of focal points, and I want you to maybe give me some ideas about how these focal points might be arrived at. Okay? So, I said usually, I get you to use your phones, don't need them. Usually use your phones to give me responses. I'm going to ask for audience participation, for want of a better word today, okay? I'm not going to ask anyone to come to the front, but I do want you to interact with me, okay? But it's all around this idea of focal points. Why are certain outcomes more likely? So, we'll start off. Here you go. That is your exam paper for summer, okay? There we go. So let's say that even at this early stage, I'm a little bit concerned. I'm not going to turn the next page over. I'm saying, wouldn't it be nice? Let's say I'm a little bit concerned about how you're going to do in this exam. So, okay, well, what I'll do is I'm going to give you a copy of this exam paper. This is hypothetical, okay? Especially because I'm recording myself also. So I'm not going to give you a copy of the exam paper. Let's say that I was, okay? So, what we've done, we're going to do something really, really clandestine. Now, certain things I can do as head of department, but giving you copies of the exam paper probably isn't one of them. So I'll say, what I'm going to do is, I can't send it by email, because that creates an electronic trail. Someone could actually see that email and track me down. So what I'll do, I'll print a hard copy of it, and I'm going to meet you on Saturday outside the Great Hall. Okay? So we've agreed to do that. Got a paper, and we'll turn up at the same time. Problem is, in my rush to tell you about the exam paper and say, look, I'm going to meet you on Saturday outside the Great Hall, I forgot to say the time. Now, we need to turn up at the same time. I can't be hanging around on Saturday with an exam paper in my hand and security guys are going to come along. Likewise, you can't be hanging around on a Saturday morning. Security guys will, well, what are you doing here? Well, I'm waiting for my lecture, come with the exam paper. That's not really going to work, okay? I've told you where we're going to meet. I've told you the day. but I forgot to say the time. And so we've gone away, and now it's occurred to me, and it's occurred to you. We need to turn up at the same time. If we don't turn up at the same time, if I turn up there and you're not there, I can't hang around, I'm going to leave. Likewise, if you turn up and I'm not there, you can't hang around, security are going to move you on. So we've got to turn up at the exact same time. So that's what I've got to think. Look, I didn't say a time. What time shall I turn up? I want to pick a time that you think I'm going to turn up. I've got to pick a time that you think that I'm going to turn up. You've got to pick a time that you think I think that you're going to turn up. Okay? So we've got to try and get into each other's minds. We've got to turn up at the same time. So I've got an idea now about what time I'm going to turn up. Okay? I should stress that absolutely there is no right answer, there is no wrong answer. So I'm not going to ask everyone. I'm just going to skirt along the front row just to get a representation of people. Okay? So, but everyone in the room do it. Everyone do exactly the same. Think about what time are you going to turn up. Of all the times you could turn up, your overriding consideration is you want to be there at the same time as me. So what do we do? I said Saturday. What next? Okay. Everyone think of what your answer is going to be. And I'm just going to take the front row here, and just so we have to answer it. No, whatever anyone says, no one change your answer. Okay? There isn't right, there isn't wrong. I just want to know what time you're going to turn up. And then I'll tell you what time I'm going to turn up. 9. In the morning or in the afternoon? Or evening? In the morning, okay, nice early start. So 9 a.m. I said no rights, no wrongs. Okay, 9. 10 in the morning. Okay. 6 p.m. Is that when you get up, is it? Yeah, okay. Mid.
10 a.m.
10 a.m. Okay.
12.
Noon. Okay.
10 a.m.
10 a.m.
12.
Noon.
No,
Yeah.
no.
11 a.m.
a.m.
9 a.m.
Oh, so it goes up.
9 a.m.
9 a.m. Okay, and 1 p.m. Okay. Bit of a mix. Shall I tell you what time I would choose first of all? Well, there are two most populous answers, and they are 10 a.m. and 12 noon. Okay? The time I chose was 12 noon. Anyone else choose 12 noon? Would have chosen 12 noon. Okay? Now you think, what have we got here? Now in itself, only, was it 2, 5, 6, 7, 8, 9, 10, 11. So 3 out of 11 chose 12 noon. So what we're looking for here, so it's not as if it's a definitive outcome. Right? But in itself that doesn't matter. But did you choose randomly? No, you think, okay, you want to choose a time that resonates with you. Why did I choose 12 noon? Well, it's the middle of the day, high noon. It's something about us that leads us towards that. So, okay, some of you did, some of you didn't. But what's the other striking feature about? So if we turn up at 12 noon, if Zach turned up at 12 noon, I turned up at 12 noon, is that a Nash equilibrium? Would either of us have an incentive to deviate? No. If I turned up at 12 and Zach turned up at 1, would we have an incentive to deviate? Yeah, both of us would. It wouldn't be a Nash equilibrium. So the Nash equilibrium here is we turn up at the same time. If either of us turns up at different, or we turn up at different times, we have an incentive to deviate. But you can see that there are multiple Nash equilibria. And what are the Nash equilibria? Well, it could be 9 o'clock in the morning. It could be 1 minute past 9. It could be 2 minutes past 9. It could be 3 minutes past 9. We could turn up at 9:15, 9:30. You can see, as long as we turn up at the same time, that is a Nash equilibrium. So there is a virtually infinite set of Nash equilibria. But what do you notice about all of those times that were quoted back? They were all on the hour. Now, I didn't say you had to meet me on the hour, but at 9 a.m., 10 a.m., 6 p.m., 12 noon, 11 a.m., 1 p.m. Did anyone choose a time that wasn't on the hour? Don't be bashful if you did. Maybe some people might, for example, chosen half past or quarter past. But all the response here, again, we've gravitated towards certain outcomes. So all of the things that we could have chosen is something in our psyche that makes certain outcomes, certain things that we can do, more likely. Again, it's another example of a focal point. So, and it's this idea, I'm going to play a few more games now just to reinforce this idea. Okay, next game is, we're going to play a game where I'm going to play, say there's one of you, and the idea is that we need to pick the same number. And this is any single digit number between 1 and 9. So if we pick the same number, we win a prize. I should really incentivise you, don't put £10 down on the table. So like, if we win it, you win that. But I'm not quite going to go that far because there's a lot of you in the room. So, but that's it. If we pick the same number, we win. If we pick different numbers, we don't win. So if we don't win, that's not a Nash equilibrium, is it? If we both pick the same number, for example, if we both picked 1, or we both picked 2, or we both picked 3, that would be a Nash equilibrium. And if we win, do we have an incentive to deviate? No. If we pick different numbers, that isn't a Nash equilibrium. I picked 1 at the same time as you picked 9. Neither of us wins. We would both have an incentive to deviate. So it can't be a Nash equilibrium. So in this game, we're going to pick any number between 1 and 9. If you pick the same number as me, we win. Those would be our Nash equilibrium. Okay? So I'll just have a quick show of hands. I'll run through the numbers. Everyone think, you want to pick the same number as me, I want to pick the same number as you. What are the numbers between 1 and 9? Okay? So think about what you think. I'm going to pick. Okay. So run through. Who's going to pick the number 1? 2? 3? 4? 5? 6? 7? 8? Anyone pick 9? 9, okay. The number I chose was, what was the most popular one here? Chose was 7. Lucky 7. 7 days of the week, 7 colours of the rainbow, 7 deadly sins, 7 wonders of the ancient world. It's just something in the number 7. Although a lot of you also picked the number 5. And why is that? Because 5 is in the middle. Again, it gives us something to gravitate towards. We're not saying that definitively these will be the outcomes, but they're saying what we're saying is something in our psyche, something in the way that we as individuals operate that lead us towards certain outcomes. And the number 7 is an example of that. However, the fact that we chose number 7 is predominantly driven by its lucky notion in Western cultures. But let's say that we change this game ever so slightly. Let's say that we're going to play the exact same game, choose a number between 1 and 9, but let's say we're going to play it in China. Now before I get you to do this game, I'll ask you a question. This might lead you to what the answer is. When was the Beijing Olympics? Oh, no one Google it. 2008. What month was it held? It was a Summer Olympics, August, well done, the 8th month. What date did it start? 8th of August. The opening ceremony, what time did it start? 8 p.m. Exactly. 8 p.m. on the 8th day of the 8th month, 2008. And why is that? Because in Chinese, you've got ba and fa. Sound very, very alike. Ba, as in number 8, and fa associated with good luck, prosperity. And so, because of that, 8 is viewed as a very auspicious number in China. So if you travel from London Heathrow to Chengdu, you travel on BA flight 88. If you go from Amsterdam to Hong Kong, you fly on KLM flight 888. Next time you're at the airport, look at the arrivals and departures. Look at the flight codes, an awful lot of flights to and from China will have 8 in them because of this idea of good luck or auspiciousness. So again, if we change that social context ever so slightly, of all of these numbers that we could have chosen in China, it's much more likely that we gravitate towards the number 8. Why do we have 888.com? What an obscure betting, gambling company to choose. It's that number 8. The Petronas Towers in Malaysia. Why are there 88 floors? It's because of this lucky number 8 in Chinese cultures. So again, if we just change this context ever so slightly, you can see we're led towards certain outcomes. Now, we're not saying there's a definitive reason for that, because after all, we're dealing with individuals and our psychology and our psyche. But why do we do certain things? Who knows? It doesn't matter. Certain outcomes are just more likely. And this particular game, we played this in China, the outcome, the Nash equilibrium that we find, is much more likely to be where both or all players choose the number 8. Now, I want to build upon this idea of social context. And I want to change that game ever so slightly. So we're not going to pick a single-digit number between 1 and 9. Again, going to play the same game where we need to choose the same number. But this is now a 3-digit number, anywhere between 100 and 999. Okay? If we pick the same number, we win. If we don't pick the same number, we don't win. As you can see, the Nash equilibrium will be where we pick the same number. You see, we all pick 100, 101, 102, 103. Those are Nash equilibrium. Yeah? So I know what number I'm going to pick. So I'm not going to run through. Who's going to pick 100? We'll have a show of hands. We'll be here forever. Okay? But everyone think of what your number is. A 3-digit number. You want to pick the same number as me. Obviously, I want to pick the same number as you. Okay? Everyone got your number? Got an idea what you'd want to choose? Yeah? Okay. The number I'm going to choose is 777. When I gave you that idea about if 7 was lucky, well, 777 is 3 times as lucky. Who chose the same number? Okay, 2, 3. So what has this done? Has it totally and utterly blown apart what I've told you? All about social contact. Well, of all the people, very, very few of you chose the same number as me. And that's exactly right. I wouldn't have given that range of numbers that you could have chosen. In fact, I'm very surprised that 3 people did choose the same number as me. What's this going to do with social context? Well, let's change it ever so slightly. Let's say rather than turning up on a Tuesday morning when you got out of bed, you didn't come down to the Bay campus to come to a game theory lecture. Rather, you turned up today to go to a convention for devil worshipping. Let's say we're just a group of Satanists. And that's the reason for coming to the room here. And now we're going to play that exact same game. And I say to you, okay, we've got to choose that 3-digit number. What would you choose? There you go. Bit of culture view there, bit of William Brake. And the number of the beast is 666. So we change the social context ever so slightly. But by changing that social context, we're then led towards a certain outcome. So, in a general sense, what number we choose, it could almost be random. But if we change the social context within which the players are playing this game, it leads us to a more likely outcome. It leads us to a focal outcome of the game. Okay. I'll rattle through just a few more. And again, it is going to pick up the idea of focal points. So, what's your name, sorry?
Cameron.
Cameron. Okay, Cameron. Pack of cards.
Right.
Okay. Same idea. Cameron and I need to pick the exact same cards. Okay, don't shout it yet. We need to pick the exact same card. I've got to think, what's Cameron going to choose? Cameron's going to think, well, what the heck am I going to choose? Okay. If we pick the same card, we win. No pressure, Cameron. Okay, what card did you choose?
Queen of Hearts.
Okay. Did you all hear that? Yeah, at the front? Yeah, it's a bit of a quiet voice. Cameron said he chose the Ace of Spades. Well then, Cameron, exactly the same as me. But, and why did I choose the Ace of Spades? It's a signature card, but probably in the same way, Cameron, that you chose the Queen of Hearts. It's just a signature card. You could have chosen the Two of Diamonds. Why didn't you choose that? Well, it doesn't stand out. Not to put you on the spot, but why did you choose the Queen of Hearts? Because of the signature card.
Pretty much.
Pretty much. Okay, well let's change the social context ever so slightly. And hopefully, you can now see what the answer to this one's going to be. Well, let's say Cameron and I were absolutely avid readers of Lewis Carroll. And we loved Alice's Adventures in Wonderland. And now we're playing this game. So, okay, now we've got to pick a card. Which one we're more likely to choose? Queen of Hearts. But it's changing that social context ever so slightly. Okay, last example then. That whilst we've mentioned social norms, and that's what dictates this. Why do we gravitate towards certain things? Why, for example, do we drive on the left-hand side of the road? Or why do we drive on the right-hand side of the road? Anyone drove here this morning? Yeah, a couple of you. Hopefully you found parking. But when you jumped in your car this morning, well, you had the option, if you really, really wanted to, you could have driven on the left-hand side of the road, or you could have driven on the right-hand side of the road. Now, hopefully, you all drove on the left-hand side. Why is that? Well, that's what people do. That's what the law says. That's what social norms dictate that we should do. Because if everyone else drives on the left-hand side of the road, and yet when you got in your car this morning, you decided to drive on the right-hand side, would that be a Nash equilibrium? No, because pretty soon you're going to crash into somebody. So you would have an incentive to change what you're doing. You will have an incentive to move towards that social norm. Do the same as everybody else. So that's what we've sort of talked about here, that social norms hypothesis. But it isn't just social norms, but it's also judgments that come into play. Okay, so our last game is, we've got £50, and I'm going to ask the volunteer, we're going to split this. Okay, £50. If we identify the same splits, we get those amounts identified. So what's your name?
James.
James. Okay, James. You go, it's £50. You could say, James says, you might have £49 and there's only £1 for me. That might be your split of that £50. And if I say, I think the split should be £49 to James and £1 to me, we've identified the same splits. So James gets his £49 and I get the £1. You might say that it's £20 to you and £30 to me. And if I say, oh, it's £30 to me and £20 to you, we win the game and we both get those shares. So when we identify the exact same split, we win. If we don't identify that same split between James and myself, we don't win. Okay? So that's the game. Okay, James. What would you say? How do you think we should split this £50?
25 each.
Are you sure? Would you rather more? No? Okay. Okay. Oh. What do you think I've chosen? There you go. So there you go. In this game, of all the outcomes that we could have chosen, no, I said to James, would you have preferred more money? You would have preferred more money. You would much rather, actually I prefer £50 as opposed to 25, but we both, exactly the same with me. We both gravitated towards this particular outcome. Now the question is, why did we do that? Of all the outcomes we could do, is it because, James, we are truly egalitarian, that we think to our very, very core that society should be equal, that we should share equally? Well, I guess this is one of these nature versus nurture questions. Is that the case? Is it because genetically, as humans, we've got this inbuilt wish to share? Or is it because James looks around the room and thinking, well, hold on, maybe everyone else in the room or society expects me to be equal? And therefore, if I say the split of this is more towards James, is towards me, does that make me appear a little bit greedy? And everyone else in the room thinks that I'm greedy? Well, it really, really doesn't matter. It doesn't matter, is it nature or nurture? The important thing is there are certain outcomes that are more likely. And that's what we found here. I can imagine with my kids, when my kids were younger, and I'd say, you are Christian, go give your brother some birthday cake, go share it with him. Imagine a kid, 4-year-old kid, they look at, what does share mean? Does it mean equal split between them? Of course it doesn't. It's young kids, they don't have these inhibitions, this social context being brought into play. They don't care what other people think, they just are concerned about what they get themselves. So again, even though I raised this in terms of nature versus nurture, it makes no difference. They are just whatever reason, and it makes no difference what they are. For whatever reason, if certain outcomes are more likely and we gravitate towards them, these outcomes that we do gravitate towards are then described as focal points. Now we've run through these games here, and that's so those outcomes, if they are more likely, they're described as focal. Now we've been through these games here, and what I want to do, very, very last thing for this morning, is bring it back round to that battle of the sexes. We said that we had the man and the woman, and we had two Nash equilibria. One where they both went to the opera, and the other where they both went to the prize fight. And I said, at this particular, or when we saw it, first of all, at that particular juncture, there was no reason for thinking either of those outcomes was more likely. Multiple Nash equilibria, we've got two of them. Which one do we choose? Who knows? In one, the woman was better off, got her most preferred outcome. In the other, the man was better off. It just changes ever so slightly though. Let's say the man and the woman, they're involved in this relationship, and the woman is the dominant personality. Now we're not saying the man doesn't want to go to the prize fight. We're not saying the man doesn't prefer to go to the prize fight. But just in their relationship, the woman is the dominant personality. But if that were the case then, isn't it much more likely that the outcome that we would observe, would be where they both went to the opera. So that extra bit of social information there, we're led towards one of the outcomes. One of the outcomes is more plausible. It's focal. And that's the holiday. It doesn't matter what causes it to be more focal, it's just certain outcomes